Okay, so this lesson we're learning a couple more points of concurrency inside of a triangle. And again, they're going to be using different segments through the triangle, so we'll get started. This lesson, we should be able to use medians to find centroids and altitudes to find orthocenters. So the first one in the lesson is the median. It says from a vertex to a midpoint on the opposite side of the triangle is a median. So when we go to construct this, again, we are focusing on from a vertice, whoops, and that was my eraser. We're focusing on from a vertice to the midpoint. And again, we're going to mark it so that it's true. It doesn't maybe necessarily measure exactly to the midpoint, but we're going to mark it with the equal number of hashes on either side. That way we know that in our eyes, it's equal on either side. So these are each midpoints along the outside. This point of concurrency is called the centroid. Now, the centroid looks a little bit different than others in regards to it's not an equal relationship from the point of concurrency necessarily back to a side or a vertex, like the circumcenter and the incenter that we learned in the previous lesson. This one has a 2/3 relationship. Now, we can look at this a lot of ways. First of all, around the whole exterior of the triangle, those are each midpoints. The other thing is, if we understand that this is a 2/3 relationship of the entire segment, we also know that this part has to be 1/3. In other words, we know that AP is going to be twice as big as PE because it has a 2/3 to 1/3 relationship. So that might be easier for us at times to identify and help us find those missing parts. Okay, so in this example, it says we have Q as the centroid, SQ is 8. We want to find QW, again, which is the 1/3 part, and then SW, which is the whole. So QW is the 1/3, and we know the 1/3 is half as big as the 2/3. So we simply take 8 divided by 2 and we get 4. Then to find the length of the whole segment SW, we can just add 8 and 4 together and get 12. So in this one, take a moment, pause, try these, see if you can identify what the missing parts are. So now that you've had an opportunity to try these, here's what you should get for your answers. PS should be 700, PC should be 1400, TC should be 2000, BC should be 1000. Excuse me, those are backwards. Sorry, BC is 2000, TC is 1000. And then PA, the 2/3 part, is 1600. PT was 800, so we add those up and we get 2400. The next thing is finding the coordinates of the centroid of the triangle with given vertices. So again, the coordinates of the centroid is going to be found by going from a midpoint of one to the opposite side of the other. So when I do this, I'm going to go 2, 5 for my first one, which is F. 4, 9, which is G. And then 6, 1, which is H. So 6, 1, there's H. Now, in order to do this, really all I need is to find the midpoint of 1. We can do the midpoint formula, or we can just count slopes. So if I count rise over run on these, my rise is up 1, 2, 3, 4 over 2. So my midpoint is going to be right there. So from my midpoint back to my vertex is going to look like that. My next segment, and again, I just need to do 2 of these. If I count the rise over the run, and again, you'll have to pardon my drawing here, but if I count the rise over the run, it's down 1, 2, 3, 4, and over 1, 2, 3, 4. So really, if I go down 2 and right 2, there's the midpoint of that segment right here. And I can go across to the vertice, and I can construct a straight line. So it looks like, if I did this correctly, That's where the midpoint of the next one will intersect too. And pardon the lines here, they got a little squiggly on me. But if I look at that segment, or excuse me, that point, it's at 1, 2, 3, 4, comma 1, 2, 3, 4. Oh, 5. So it looks like it's at 4, comma 5. So essentially we could use the midpoint formula and draw a line straight to the other segment, or we could use the slopes of the lines themselves. For the sake of keeping the video short, I'm going to go ahead and skip the next one. You guys can sure ask about that one in class, and I'd be happy to show you the next one. Using the altitude of a triangle, we are going to construct our next one. Now, the altitude is the height of a triangle. The one thing I want to draw your attention to here is if our triangle is acute or right, the height of the triangle is inside or on the triangle, whereas if it's obtuse, the height of the triangle is technically given by the distance from the vertice straight down to the opposite side. And that's weird. I don't know why that drew a circle. But it's straight down to the opposite side that falls outside of the triangle. So the orthocenter, again, is the altitude. So it's from the vertice straight to the other side. And again, it's a little difficult to see, but it's from the vertice straight to the other side, and from the vertice, and this one nearly looks right, straight to the other side. But those are all meeting at right angles. This is the one triangle that I feel like your book might actually do a better job of illustrating, is this orthocenter. Now, the nice thing about the orthocenter is it's just the intersection of the altitudes. There's no congruence relationship. There's nothing that we really gain from knowing it other than the fact that it's called the orthocenter when the altitudes meet. So the other thing that we know about the orthocenter is that it can either fall on the triangle, inside if it's acute, and outside if it's a right angle. The one thing to note on this one with the orthocenter, much like the circumcenter, whereas it can fall on the triangle, the only difference was the circumcenter would fall on the hypotenuse. The orthocenter falls on the right angle itself. That's the main difference there. Okay, but the two that can fall outside the triangle are the circumcenter and the orthocenter. So again, in this one, we have a triangle XYZ with vertices at -5, -1. So there's X. Our next vertice is at -2, 4. There's Y. And then Z is at 3, 1. Now, when I go to construct my triangle, if I look at the slopes of my lines, that's going to tell me a lot about my orthocenter right away. And I'll try and draw this one a little bit straighter. So if I look at the slopes of my lines and I count rise over run, if I find that they're perpendicular, I know my orthocenter is going to be on this angle, but otherwise it's going to be really close to it. So if I count rise from -1 up to +4, my rise is 5. My run is from -5 to -2, which is 3. So rise over run gives me up 5 over 3. Now, if I look at the rise over run for my other equation, from y, my y is 4, down to -1 I should have put that down. It's 3, -1. It's right here. Sorry. That might make it a little easier. We'll see if we can't make this work. There we go. Perfect. So if I count here, now we're back on the right track. So if I count, I go down from 4 down to -1, and then over from -2 to +3. So my slope is down it looks like this is going to be my orthocenter right here. And I need to double check this one, guys. Pardon the notes. I will tell you right up front, if there is one of these on the homework, I'll help you out with it. but I think my graph here, and I'm trying to hustle my video along, is a little off. Yep, that's true. I need to do this a little bit differently. So wait until I'm in person in class to ask questions on this one, and I'll sure go over that one with you, okay? So we're going to skip these for now and come back to them. But I do want to draw your attention to this before the end of the video. So we have those 4 main segments inside the triangle and the 4 points of concurrency on the right there. This is a huge piece of information for your test. So please, please, please pause the video. Make sure you get that in your notes. So again, I'll go back over those orthocenter questions in person. Those are a little complex, but again, make sure we get down this little core concept box here, and that's the big important thing for the video. Thanks, guys.